Hello, welcome to my talk on why Reynolds number is so important in fluid dynamics. Here, I will use a simple example of a pipe flow to show how to use Reynolds number to simplify the fluid dynamics problem. In fact, the way to represent the result in this example is universal, as we have seen in many other textbooks and publications for other fluid dynamics problems. The example here is the famous viscous flow in a horizontal pipe, and we will see how we can use the dimensional analysis method, that is, the Buckingham Pi theorem, to simplify the fluid dynamics problem. The example seems quite simple. A horizontal pipe of a diameter d with a pipe wall roughness epsilon. Suppose the average flow velocity is v and the fluid density ρ, viscosity μ. The question is to find the fluid friction for the flow in the pipe. In fact, the problem can be quite complicated. It is very dependent on the flow Reynolds number. As we all know, when the pipe flow velocity is very small and the corresponding Reynolds number is less than 2,300, the flow can be nominal. And such a flow is axisymmetric, hence it can be regarded as a 2D flow, and we can solve the Navier-Stokes equation directly to obtain the flow. And this flow is the famous Hagen-Poiseuille flow. And from the solution we can calculate the flow friction. However, when the flow velocity is large, and the corresponding Reynolds number is very large, say more than 10 million, and the flow would be fully turbulent, and there is no analytic solution for such a flow. In such a case, it can be studied using the experiment or numeric modeling. But for both approaches, we may need to find what is the best way to carry out the study, and what is the best way to present the result. The methodology is the Buckingham Pi theorem. If you are interested, you can watch my talk on dimensional analysis principle. Here, we will use the theorem to simplify the problem. The first step is to analyze the problem, and we need to determine what the parameter might have influence on the fluid friction. From the experience and intuition, the fluid friction may be affected by the following parameters. Flow velocity. A large flow velocity will cause a large fluid friction. The fluid viscosity would have a large influence on the fluid friction. Fluid density may be an important parameter for the fluid friction. The pipe diameter. For a large diameter, the fluid friction would be larger. And the pipe wall roughness. This may be important for the fluid friction, especially for the turbulence flows. From the analysis above, the fluid friction Fr can be expressed as a general function of 5 physical parameters: velocity, viscosity, density, diameter, and the wall roughness. And from this expression, we can see the total variables, including the friction, would be 6, so n equaling to 6. Here now, we might have a problem, how we can best study the problem and how we can present the result. For instance, if we look at the fraction change in different velocity, and we can see the curve as this. These 4 different curves for 4 different pipe wall roughness, epsilon 1 to epsilon 4. And if we consider the inference from the pipe diameter d, and we should have the 3-dimensional plot. So these 4 curves for D1 and these 4 curves for D2. However, if we consider the different viscosity, different density, the problem would become very complicated. And in that case, we might need a lot of such plot for different viscosity, different density. Therefore, we can see the problem if we use the direct way to study the problem. Luckily, we have the Buckingham pi theorem for us to simplify the problem. Here, in the step 2, to choose the base unit involving in the dynamic system, as well as for most other fluid dynamic problems, the base unit will be used as the mass, the symbol m, and the unit kg, the length, the symbol L, and the unit meter, and the time, the symbol T, the unit second. Why we choose this 3 base units? That's because these 3 base units can be used for defining the motions, forces, moment, mechanical energy, etc. If the thermal energy is involved, then we might need another base unit, temperature, capital theta, and unit K, Kelvin. But this would be beyond the scope of this talk. For instance, the force has the symbol unit Newton, but it is a derived unit given by a combination of the base units mass, length, and time. So the dimension can be expressed as ml t power of minus 2. So in the third step, the dimensions of all 6 variables are analyzed, given in this table. So it can be seen that all these 6 variables can be expressed using these 3 base units, and the corresponding symbols for the variables are given in the dimensions here. So if we take some simple parameters, for instance, the velocity, its unit is meters per second. So this dimension is given as this. And for the density, its unit is kg per meters cubic. So its dimension is given by this. And for the diameter, it is the simplest. It has a dimension same as the base unit length. Its dimension is given simply by L. So if you are interested, you can work out the dimensions for other parameters here. So in the step 4, we use the total number of the variables n equaling to 6 and the number of the base dimensions m equaling to 3. Here we might have a problem how we can choose the constructing parameters to represent the base dimensions. Since we have 3 base units in the dynamic system, therefore we have to choose 3 constructing variables from the variables here, the total variables. And the number is only 3, no more, no less. And for the constructing variables, they must include all the dimensions for the 3 base units, mass, length, and time. Again, no more, no less. But how we can do this? Obviously, for the length, we can choose the pipe diameter d. It has a unit m, same as the length. But for the mass m, the unit kg, we choose the density rho, unit kg or meters cubic. But we can construct the expression rho d cubic, so it has the unit kg. And for time t, unit second, we choose the velocity, unit of meters per second. But we can construct the time, use d divided by v, so we have the unit second. Here I would say these three chosen constructing variables, the diameter or the length, the density, and the velocity are always correct as the constructing variables for most of the fluid dynamic problems. Next, we need to look at the number of the non-dimensional parameter. So here we calculate n minus n equaling to 3. That means we have 3 non-dimensional parameters, 3 pi's. In the step 5, we can construct 3 non-dimensional parameters, pi 1, pi 2, and pi 3 as this. And here we can see in the brackets, the velocity, density, and the diameter are chosen as the constructing variables for this non-dimensional pi's. Pi 1 would corresponding to the flow friction, and the pi 2 would correspond to the fluid viscosity, and the last one would correspond to the pipe roughness. And next step, we would use the dimensional analysis to decide the power indices here, A, B, C, D, E, F, and P, Q, R. Here, we take the second non-dimensional parameter, pi 2, as an example. In the dimension analysis, we replace the variables with their dimensions as this. And we will have the expression as this. Now we can match the power indices for a non-dimensional parameter given by this. All the power indices would be 0. So we can build the equations for the power indices D, E, F. And solving all this equation, we can obtain the power indices D equaling to -1, E equaling to -1, and F equaling to -1. Therefore, we can construct the non-dimensional pi 2 given as this. However, in practice, the inverse of this non-dimensional parameter pi 2 is generally used, which is actually a non-dimensional variable Reynolds used in his publication as the K number in 1895 when he studied the pipe flow transition from laminar to turbulent. And now this non-dimensional parameter was named as Reynolds number as we used today, given by this. Following the same methodology, we can obtain the first non-dimensional parameter pi 1 for the fluid friction, and the expression of the non-dimensional parameter pi 1 would be given as this. This is actually the friction coefficient, CF, given as this. And in a general application, d squared here would be replaced using an area S, both d squared and s have same unit, meter squared. Similarly, for the third non-dimensional parameter, pi3, which is constructed with the paper wall roughness epsilon, and use the dimensional analysis, we can solve the power indices P, Q, R, and we can obtain the expression for the non-dimensional parameter pi3 as this. And this non-dimensional parameter is the relative roughness of the paper wall. Now we can see the original function of the fluid friction has been expressed as a function of 5 variables: velocity, viscosity, density, diameter, and the wall roughness. But after the dimensional analysis, the non-dimensional fluid friction can be expressed as a function of 2 non-dimensional parameters as this. And more specifically, this expression can be expressed as the friction coefficient CF as a function of the Reynolds number and the relative roughness of the paper wall. So we can see such a way the problem can be much simplified after using the dimensional analysis. Now the problem can be present in this plot, and this plot would give us all the necessary information we need for the paper flow friction. So we can see when the Reynolds number is small, the flow is nominal, so the friction coefficient is given as this. And when the Reynolds number is very large, the flow is fully turbulent. The fluid friction coefficient would be constant, see here. From this plot, we can find out what is the CF, and based on this expression, we can calculate the fluid friction FR easily. A more significant simplification can be seen if the pipe is smooth. For instance, for the very popular PVC pipes. In such a case, the wall roughness would not be a parameter for the fluid friction. As such, the friction coefficient CF would be the function of Reynolds number only, and the result can be present as this simple plot. So here we can see the huge advantage of the expression after the dimensional analysis. And again, once the fluid condition is given, the Reynolds number can be easily calculated, and so can the friction coefficient CF. And we can then obtain the friction using the same formula in the previous slide. And in this plot, we can also see if the flow is fully turbulent at a very high Reynolds number, the friction coefficient becomes a constant. And this would be very useful since we can easily extrapolate this to a high Reynolds number with very high confidence. The same principle is also used for the blue path airfoils. Here we show some experiment result for the airfoil LACA 23012. So for the lift coefficient CL, we have the experiment data given in this plot. And we can see the lift is given in the lift coefficient, the long-dimensional expression for the lift. But when the angle of attack is small, the Reynolds number would not have much influence to the lift coefficient. However, when the angle of attack is larger, for instance larger than 15 degrees, and we can see the Reynolds number has big influence on the lift coefficient. And the larger the Reynolds number, the higher maximum of the lift coefficient. From this plot, we can easily decide the CL, and we can use the expression here to get the airfoil lift. This is the plot for the drag coefficient of the airfoil, and we can see the quite large difference for different Reynolds number. The larger of the Reynolds number, the smallest drag coefficient would be. And again, if we can obtain the drag coefficient, then we can calculate the drag using this formula. So all these principles are very similar to the principle we present in this talk.